Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 30th, 2025, about 4 days ago. It introduces a novel mechanism called long cat zigzag attention that scales large language models to 1 million tokens, achieving a 90% reduction in decode costs compared to Flash MLA. The paper is titled Efficient Context Scaling with Long Cat Zigzag Attention. And as we'll see later, the results on long context benchmarks are really impressive. Figure 1 lays out the long cat zigzag attention method. The left side depicts the backbone architecture, which stacks feed-forward networks and mixture of experts layers. The real innovation appears in the green panels on the right. The top panel shows a calibration step where the model learns a parameter, alpha, to weigh the importance of standard multi-head latent attention against the faster streaming sparse attention. Then, as shown in the bottom panel, the layer fully converts to the sparse mechanism during training, which drives the efficiency gains. So, while Figure 1 outlined the theory, Table 1 provides the pilot study data that justified those design choices. It tracks performance across standard tasks and the long context, long eval benchmark. The baseline long cat flash starts high, but look at the second row. Naively using an interleaved sparse pattern crashes the long eval score down to about 54%. In contrast, the final row shows that using the calibrated sparse pattern, where the model intelligently picks layers, recovers the score to nearly 90%, confirming why calibration is essential. Okay, having validated the calibration strategy, Table 3 now pits the final chat model against strong competitors like GLM 4.6 and DeepSeek V 3.2. If you look at the general section, the sparse model, in the far right column, holds its ground against the dense baseline, with MMLU scores staying effectively flat around 90%. However, the dramatic improvements appear in the long context rows at the bottom. Here, the new model leaps ahead of the baseline, raising the MRCR score from roughly 34 up to nearly 60. It also excels in the math section, achieving the highest score on the challenging Beyond AIM benchmark. Well, while the chat results were impressive, Table 2 checks if the underlying base model holds up. It compares the standard long cat flashbase in the top row against the new experimental version in the bottom row. For general tasks like MMLU Pro and GSM 8K, the performance is practically identical, showing that sparsification causes no loss in reasoning power. However, looking at the long eval column on the right, the sparse model actually boosts accuracy, rising from roughly 96% to over 99%. So, validating that 1 million token capability is the focus of Figure 2. It compares the chat model, plotted in green, against the competitive QN3 baseline in purple, measuring performance on the multi-reference context retrieval task. In the left panel, which tracks the two-needle test, notice how the green line stays robust even as the context stretches to 1 million tokens. While the baseline dips after 256K, the long cat model maintains a higher area under the curve. The right panel confirms this advantage on the harder 8-needle task, where the model again leads across longer sequences. Alright, Figure 2 proved the model works at long range. Now Figure 3 demonstrates the efficiency gains that come with it. These charts plot the relative speedup of the experimental model, in green, against the baseline in blue, across increasing token counts. In the left panel, which measures the prefill phase, the speedup climbs steadily as the context length increases. By the time we reach 256K tokens, the sparse model is over 50% faster. The right panel shows a similar trend for decoding, where the experimental model delivers nearly a 1.5 times speedup at the longest measured context, confirming the computational savings. So, while Figure 3 showed system-level gains, Figure 4 zooms in specifically on the decode kernel cost. The blue bars show the cost of full attention rising steadily as the context length extends to 256K. In contrast, the green bars for streaming sparse attention remain almost constant. This divergence results in a massive efficiency advantage at long contexts, where the sparse kernel becomes nearly 17 times cheaper to run. Wrapping up, the big takeaway is that we can break the cost barrier for long contexts without losing quality. By intelligently selecting layers to sparsify, this method enables 1 million token reasoning while slashing kernel costs by 90%. It suggests that calibrated sparsity is the future of efficient modeling. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.